Yeah, so here we are. We're going to create a linear model for this table, which shows the concentration of carbon dioxide in the Earth's atmosphere, which is measured by scientists. This is real data. And this concentration is measured as parts per million. So it really means that in 1976, if you had a million parts of oxygen, 332 of those million parts would have been carbon dioxide. And by the year 2002, that was up to 373 parts per million. So if I've already graphed the dots here, and I already scaled the axis, and I'm going to talk about that in a moment. But I just did this because I didn't want to spend a lot of time on it. And you can see that this scatter plot shows very, very, very strong linear correlation. So we're going to use a line to model this. So you can see that I scaled the x-axis just using years, and I used my little squiggle here, this little squiggle. Let's use a different color. Yeah, this color here. There we go. My little squiggle. That just means that I skipped from year 0 to year 1976. Because obviously, I don't have any data before 1976, so I skipped it. And the same with here. I skipped from 0 parts per million, because that's never really existed. There's always been some carbon dioxide in our atmosphere to 330 parts per million, because that's what I care about. So I did the little squiggle. And, I could just go by every 2 years here, because that was pretty simple. And that matches the table. But my parts per million, I had to do a little bit of math to figure that out, how I was going to scale the y-axis. So what I did was I looked at my biggest value, 373, and I subtracted my smallest value, that's 332. And of course, oh goodness gracious, here we go. And of course, that's 41 parts per million. And I also know that I had I had 15 lines to go here. And so I can't go by 2s because I'd only get to 30. So I decided that the best course of action was to go by 4s. And then I knew that I would get, well beyond what I needed. So I went by 4s, starting at 330, and then you can see I went up by 4s. So that's how I chose to scale my y-axis. Now you can choose to do it differently, but you have to make sure that the jump between each and every line is the same amount. I went from 330 to 334, and then 338, and so on. So that now that we've got the line made, our next job is to make a fit, or I'm sorry, we didn't make a line. Now that we've got the points plotted, our next job is to make a fit line. And a fit line, as we know, needs to have a few things. It needs to follow the trend of the data. It needs to go through the middle of all of the data. And it's really nice if it can touch two of the points at least. Now, if you look at these points, they're so close together that this is really not going to be a challenge to do. I can actually make this line that I'm drawing here touch basically every single point. And I'm going to say that that's a pretty good fit line. Now, I have, well, actually, that's not a good fit line. So let's try that again. Because, look, I have 1, 2, 3, 4, 5 dots above it, and really none below it. So let's try one more time if I'm going to be a really precise mathematician. All right. Oh, one more time. Maybe. Okay. All right. Now I've got some dots above and some below, and it's obviously going through a few of those dots. But now if I'm gonna find the slope of the line, I need to choose a couple points that are definitely on the line. So I think that this point 1984, oops, wrong tool now. Here we go. Okay, this point here, 1984, that's definitely on the line. And I can find this other point, 1996. Yeah, that's definitely on the line. And I have those 2 points here. There's 1984, there were 344 parts per million, and in 1996 that had risen to 363 parts per million. So my next task is to figure out, well, how fast is this increasing? So we've scaled the axis. We've already described the correlation, and we'll just write it here. It's a strong positive correlation. Okay, cool. But now if we're gonna create our slope, we should find, or if we're gonna find the slope of the line, we gotta use 2 points. So those 2 points were 1984. Let me see here, 1984, and there were 344 parts per million. But then by 19 1996, that number had grown to 363 parts per million. So now I need to use the slope formula to find the slope there. So remember, the slope formula is really, we're just trying to figure out how much did the y change and how much did the x change. And then we use division. And so really I'm figuring out, how much did the parts per million grow and how long did it take? And then I use division to sort of convert that to a unit rate. So I went from 344 to 363 parts per million, but I'm going to use subtraction here. And I'm just using the slope formula, y2 minus y1. See, I have y2 is 363, y1 is 344. And it turns out that the difference between those two values is 19 parts per million. So that means it grew 19 parts per million in that time frame. And that was in 1984, so I'm just going to leave the 19s off. I'm going to say that they went from 1996 to 1984, and that was a difference of 12 years. So we could say that it grew 19 parts per million over the course of 12 years, but if we want to convert that to a unit rate, that's about 1.58 parts per million each year. Okay? Well, I just described that in words, so now I'll write a sentence. The slope means, so when you write a sentence, you should always start with an introduction. The slope means that CO2 is rising by 1.58 parts per million each year, something like that. So now we're going to write the equation for this thing in point slope form, okay? And we know the slope, that's 1.58, and we have two different points that we can choose from, 0.1 or 0.2. And I'm just going to use 0.1 because I'm a linear thinker. So point slope form, you should have it by now, but it's m, so 1.58 times the different x minus the x coordinate. Remember, if I plugged a 1984 into this, to this part of the equation, this would turn this whole thing into 0. 1984 minus 1984 is 0, times 1.58, still 0. Okay? So if I plug 1984 in, that part of my solution, I would get 0. So in order for it to stay a solution, I'd need to add 344 to it. So now 1984 and 344 is a solution. Okay? So that's my equation in point slope form, and I'm going to use that for my model for the rest of this problem. So that's the bulk of the work. Everything else is pretty easy. So all we have to do now is just keep using this equation to make other predictions. So part F says, okay, now let's use our equation to predict the concentration of carbon dioxide in this year, in the year 2017. I have an equation, and I know that Y stands for the parts per million. I know what X stands for. That's the years. And the thing that I know now is that my X is 2017. So why don't I just take that and replace the x in my equation like this. So I'm going to say y equals 1.58 times 2017 minus 1984. But then, of course, I need to add 344 to that. And so I'm going to show all my work here. 1.58. Now, 2017 minus 1984 is 33 years, which means it's been 33 years since Reagan was elected to his second term. Wow. For all the middle schoolers out there. All right, so now I'm going to multiply 1.58 times 33. That's my next step. And I'll get 52.25. So we could say that in those 33 years, we'd expect, we don't know, but we'd expect that the carbon dioxide has gone up by 52.25 parts per million. But we were already at 344 in that time, so when we add those two things together, what we end up seeing is we got about 396.25 parts per million here in this year 2017. Uh-oh, getting hotter. So now, finally, the scientists estimate that the Earth's environment can only sustain itself up to 600 parts per million. So if this trend continues, in what year will this occur? And we're supposed to use our equation. Well, again, y is parts per million. So let's just replace y in our original equation. Never change your original equation. Our original equation was y equals 1.58 times x minus 1984 plus 344. So I'm just replacing y with 600. And I'm going to write everything else. just the way that it's written. Didn't change anything except the letter y. Now, we're going to solve for x. And, you know, I bet a lot of people would want to use the distributive property on this equation, but I'm going to do something different. I prefer a different method, which is first I'm going to just subtract the 344 from each side, like this. So 600 minus 344 means what we're really thinking about here is, well, how many parts per million would be added since 1984 until we get there? And so that turns out that's a difference of 256 parts per million. So I really want to know, like, so how long does it take at this rate for the Earth, or for us to add 256 parts per million to our atmosphere? And so now I know the rate is 1.58, and if you just stop and think about it, this is a multiplication. So why don't we just use division to undo the multiplication? So I'll divide both sides by the slope, by the rate, 1.58. And when I do that, well, these things are gone. And in order to grow by 256 parts per million at 1.58 parts per million each year, that's going to take approximately, now I'm going to round here, but it's approximately 162 years for that to happen. And that's a long time, right? So it's not so bad. But that's 162 years after 1984, which is why, since I'm isolating x, the next thing I do is I add 1984 to each side. And by adding 1984, I'm just basically, I'm adding the year to the number of years. This is the 162 is the number of years to add 256 parts per million. And when I add those things together, it turns out that that's 2146, which is a year, right? That's the year 2146, which is in about 129 years, I think. So anyway, that's a way that we can, remember we went back from just a table here at the top. We had a table of data. We plotted that data. We made a line, and then we used that line to make predictions. And that is what we actually use mathematics for. We take data, we create a model, and we make predictions.